You're scrolling through your feed and boom, you stop dead in your tracks. You're looking at what seems like a massive, big-budget Hollywood production, only to realize it was completely AI-generated. But then, literally 2 posts down, you see another AI video where a person's fingers are somehow melting into a coffee cup and the background is just this morphine, jelly-like mess. Today, we're solving that mystery. We're going to break down the exact science and orchestration behind why platforms like Higgsfield are producing these breathtakingly cinematic outputs, while others are still struggling with basic, everyday physics.
So why do some AI videos look incredibly real, while others morph unpredictably? That's the million-dollar question, isn't it? Producing coherent AI video isn't just about stringing together some pretty pictures. It is a massive, incredibly complex engineering hurdle. Think about it. You're asking a computer to calculate appearance, lighting, spatial geometry, identity, and temporal physics, all at the exact same time.
So the crucial point is really how you approach that engineering hurdle. The old-school way relies on a raw, single AI model. You feed it a text prompt, and it acts like a giant black box, just guessing everything at once. Because it gets totally overwhelmed with ambiguity, tiny little errors start compounding, frame by frame. But the modern solution, it's completely different. An orchestrated system doesn't rely on one model guessing in the dark. It uses a constrained, structured pipeline that honestly mimics a real-world film crew. Okay, let's dive into this roadmap. We'll start by tackling the AI video problem, then look at the Latent Diffusion Engine, check out the cinematic logic layer, explore virtual optics and cameras, lock down identity and physics consistency, and finally, put it all together in the full orchestration pipeline.
Section 1. The AI video problem.
All right, before we can really appreciate the cinematic polish, we have to understand the nightmare of generating raw video. When you give a standard text-to-video model a vague prompt, you're essentially throwing it into a high-dimensional nightmare. It has to somehow figure out what objects look like, how light bounces off of them, and how gravity affects them across time in a single pass. Because it has to solve all of that simultaneously, a microscopic math error in frame 1 balloons into a massive, bizarre distortion by frame 20. That's exactly where that jittery, jelly-like look comes from.
Moving on to Section 2, the Latent Diffusion Engine.
Let's look under the hood at the foundational math that's actually generating the pixels. Think of this engine like a system that's slowly revealing a perfectly coherent movie out of pure static. Step 1 is compression. Using a 3D variational autoencoder, it squeezes the video down into a highly compressed latent space. Step 2, it slices that space into discrete little blocks called spacetime tokens. Finally, in Step 3, a transformer steps in to slowly denoise those tokens, step by step, referencing the other tokens to figure out what the video is actually supposed to look like.
Now, what's really interesting here is how these spacetime tokens function. Because they represent both space and time, the transformer uses something called temporal self-attention. This basically forces tokens across different frames to talk to each other and share continuity. So if a car is moving 50 miles per hour in frame 1, the system remembers that physical momentum in frame 30.
But how it calculates that motion matters tremendously. Older video models used curved Brownian trajectories. That required over 50 denoising steps, and taking that long curved path caused heavy motion drift. Everything would warp. Modern engines, though, use rectified flow paths. They learn a straight-line probability path from static noise to the final video. Straight lines totally eliminate that directional drift, keeping your video incredibly coherent in just 4 to 8 steps. It's a massive upgrade.
Which brings us to Section 3, the cinematic logic layer.
This is where we step away from the raw math and introduce the director of our AI film crew. To quote the underlying theory, by reducing ambiguity before generation starts, the diffusion process operates inside a much tighter, more coherent distribution. Basically, an AI model hates ambiguity. So before a single pixel is ever generated, an LLM acts as an automated text director. You give it a simple prompt, and it expands that into a highly structured shot list, a pacing plan, and a lighting setup. It drastically reduces the entropy the model has to resolve.
Next up, Section 4, Virtual Optics and Cameras.
If the logic layer is the director, this is the cinematographer. And this brilliantly illustrates why text alone just isn't enough. If you type a weak prompt like pan right into a standard model, it just guesses what panning looks like and usually ends up dragging the subject right along with the background. But cinematic systems use explicit geometric constraints. They decouple the camera's motion from the subject's movement by injecting actual 3D trajectory math right into the attention layers.
They do this using heavy math like Plucker ray parameterization. I know, that sounds incredibly dense, but here's all you really need to know. It's a 6D coordinate system that acts as rigid math for the virtual camera. By forcing the AI to obey these specific geometric rays, the parallax and background shifts follow actual rigid body physics. It completely stops the background from wobbling or warping when the virtual camera moves.
All right, Section 5, Identity and Physics Consistency.
Now let's visit the casting and wardrobe department. One of the absolute hardest things in AI video is keeping a character looking like themselves when the action kicks off. Advanced systems pull this off using decoupled cross-attention. Tools like Soul ID extract a frozen identity signature of your character and then inject it into the model through a totally separate pathway from the text prompt. This means you can prompt a super heavy action scene, and those action words won't accidentally distort your character's face or proportions.
Finally, Section 6, the full orchestration pipeline. Let's bring all these departments together. A truly cinematic platform doesn't just use one giant brain to do everything. It uses a multimodal router. Different models have different specialties, known as inductive biases. If your shot needs synchronized sound and a long continuous take, the router sends it to Cdance. Need incredibly realistic human motion and momentum, that goes to Kling. Want high-fidelity, atmospheric outdoor scenes? It routes to Veo. It assigns every task to a specialized expert. And because of this intense specialization, models like Cdance can natively handle up to 30-second continuous takes. By expanding the temporal attention context window, it can run these massive sequences in a single forward pass without degrading into a pixelated mess. It's wildly impressive.
Let's move to the final step and see how this builds into the pristine output you actually watch. Generating 4K video all at once will literally crash a system's memory, so it cascades. Step 1 is base synthesis. A low-res diffusion transformer calculates the global motion in physics. Then comes Step 2, temporal super-resolution. A dedicated upscaler synthesizes the high-frequency details, like skin pores or the actual weave of a fabric. Calculating motion first and polishing textures last completely prevents that annoying flickering effect.
So, let's summarize this entire cinematic pipeline. Flawless AI video is an orchestration. You start with upstream logic and planning to kill ambiguity. You lock in the camera with geometric conditioning. You freeze the characters with identity memory banks. You route the task to a specialized model, and you finish it with cascaded upscaling polish. All these departments working in perfect harmony.
Which brings us to our final thought. The magic isn't just a better algorithm, it's the architecture surrounding it. Next time you see an unbelievably flawless AI video scroll past your feed, ask yourself, was it just a raw model getting lucky, or are you actually looking at the invisible hand of an entirely orchestrated system? Thanks for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.